Меня зовут Ivan. According to something that I read, я разработчик в KDE. I guess I completely mispronounced it, but who cares? I can apologize. The past time I was in Moscow, I said, извините, пожалуйста, что мое представление в английском языке. I'm not going to repeat all the sentences that I prepared back then. So, if you want to ask questions, you can ask questions at any time. Please ask them in English or try to speak really slowly. So I usually tend to start presentations by making a few disclaimers. The first one is my favorite quote from Phil Wadla. You should make your code readable because somebody who works on your code afterwards might be a psychotic killer. And obviously he will know where you're living. And the second disclaimer is that obviously the code in the slides is usually not really production-ready code. I've omitted std namespace. I don't tend to use references in the slides, maybe sometimes. Just slides are meant for clarity, and obviously I expect everybody here to be able to decide which way to pass a variable to a function would be the best. Okay, so a little introduction about what functional programming is before I switch to the next slide. There is an anecdote that if you find two functional programmers and you ask them, so what is functional programming, you're going to get 3 different answers. Because usually you always think that the language that you're using is the functional one. So whatever language you're using, exactly those features make a functional programming language. And because lately Haskell is one of the most popular FP languages in the world, usually the terms connected with functional programming are higher order functions, purity, mutable state, laziness, and similar stuff, and strict typing. But the problem, if you say that all of those are requirements, then there will be only one functional programming language in the world, and that is Haskell. So you will just remove Lisp, which is the first language. From the list, you are going to remove Ericsson's Erlang and a lot of other popular languages because you just tailored your definition according to one. From my point of view, I'm not a purist, so I tend not to over-define stuff. The only thing that I require a language to have in order to be functional are higher order functions. So, do we all know what higher order functions are? Who doesn't? Okay, so if you have a function that can accept another function as its argument, or a function that can return a new function, that's a higher order function. So you're not just passing the regular values to a function, but you can also pass functions. Can anybody tell me an example from C++ of what a higher order function is? Okay, we can pass lambdas around. I wanted something that is available even in C++ 98. std accumulate. Any algorithm in the standard library accepts either a predicate or a comparison or a function or anything else. std transform accepts any type of function, unary function. So we have already we have had higher order functions in C++ since C++ was standardized. So in essence, C++ has always been and always will be, after all, and a functional programming language. So it's multi-paradigm language. It has object orientation. It has support for generic programming, for functional programming, and who knows what else. And I'm going to tell you a little bit of a story how I got into functional programming in the first place. A long time ago, when I was, I think, in later elementary school, I had a little bit to earn my living, and I used Linux, and obviously all people who order you to make programs, they use Windows. And because of that, I didn't want to have a Windows machine, so I tried to find a language that I can compile on one machine and it works on another. And I'm not going to mention the name of that language because I hate it so much. So I guess you all know about what language I'm talking about. So in some version of that language, after I already got fed up with it, they had a huge marketing. And they said, okay, this version will be the best version of any programming language. We added a for each loop to it. We added a try with resource, which automatically frees your data when you exit a try catch block. And again, the second thing is really crappy because in C++ we have these structures. But the for each loop we didn't really have. But again, a lot of libraries provided us with a macro that does the same thing because the language is just more extensible than this language far, far away. So in STL we had the algorithm std for each, which had the awful syntax, but it did the same. And then we had in Boost or Qt, we had the for each macros. So the reason why I first started investigating functional programming languages is that instead of having to make things like this core language features, you can just create a function that does it. And you can always extend the programming language that you're working in without waiting for the standards committee to pass a new feature into the compiler. A lot of stuff can be done just in the library. Okay, that's what I just said. So examples from C++ 98, we had find if, we had bind first, evolved into bind. We had in Boost for each. So we had a lot of high order functions and we should have used it daily. I know a lot of C++ developers who don't know what STL is, but you're not them. So the only prerequisite why C++ is a functional programming language is that it supports the call operator and it has templates, which allow us to use any object that has a call operator as if it was a function. And if something behaves like a duck and if something quacks like a duck, it's a duck, right? So if something behaves like a function, it's a function. So the first level of functional stuff, functional idioms usage in C++, I decided to call abuse. Because it's, again, it will not be functional programming, but you will use some functional stuff to implement extensions of the language. Just as a simple example, we all know what lazy evaluation is. Deferred evaluation. Who doesn't? Okay, so we want to have something that looks like a normal block in C++. We are defining a variable that when we ask it for its value, it will evaluate the block, and then the result will be stored in that variable for later use. So if we don't, if the right answer is false, we are not going to ever evaluate this block of code. And if somebody tries to get the value of answer multiple times, again, at most once, we will evaluate the block. So if we wanted to create something like this, we need to create a wrapper. This definitely cannot, the type of the answer is not an int. We need to have some kind of handler to an int. So we are going to create a template class, for example, called lazyval. Inside of it, we need to store the functional object, which that block will be. And at some point, we'll have to evaluate it and save its result somewhere. Now, because lazyval needs to save the value. It needs to have a mutex in order to lock, to synchronize stuff so that if two threads try to evaluate the same thing at the same time, you don't get into trouble. And we need to be able to save the value if we calculated it. So there are two approaches to this, to solving the idea whether do we have the value or not. One is the usual, the old school. We have a bool and we have an instance of type T. The problem with a bool and an instance of type T is that it requires T to be default constructible, because at first we can't initialize it to anything sane because we don't have the value yet. Instead of it, the proper way to do it, which supports non-default constructible types and which documents your code quite well, is to use optional. Who doesn't know what optional is? So just imagine optional as a little box that can either contain a value. So for example, if this is optional of int, it's either an empty box or it's a box that contains just one int. So like having a list that has at most one element. If you don't have the value, it's empty. If you have the value, you put it in the box. And std namespace got optional quite recently. In Boost, you have it for quite a long time. The nice thing about optional compared to, for example, a pointer or something like that is that optional owns the data, so automatically disposes of it. You don't need to think about new and deletes and everything else. So here we have created all of the data that we need to store in the lazy val. The only thing that is rest is to declare the cast operator to the type that should be the return type of the function stored in the lazy val. So instead of having a .get or anything else, we just create a cast operator or operator that can convert the lazy val into its actual contained type. And it doesn't do anything particularly smart. It just logs the current scope, so logs the mutex, checks, do I already have the value? If I don't, I'm going to call the function and remember the value. And then we're going to return, if we already had the value, we're going to return the result. And if we didn't have the value, we are not going to return it. We're going to evaluate it and then return the result.
Sorry, one question. Why we should use invoke here? We can just invoke a function with the usual operator.
Okay. Thank you. That's something that I wanted to skip and to check whether anybody will notice. And can you just approach the podium a bit? I have a gift for you. So invoke, do we all know what invoke does? So who doesn't? Invoke is a generic function. So in C++, we have a few of different objects that we can call as functions. So for example, if you have a normal function, a function pointer, function reference, if you have an object that has the call operator, if you have an object that can be converted to a function pointer, etc., you can call it as f open parentheses, close parentheses. But those are not the only things that look like functions in C++. For example, member functions and member variables. They all receive arguments, some of them implicit as this, and they return a result. And we can't actually write ampersand class : something of some instance. So because the core language doesn't allow us to call member functions actually as a freestanding function, unfortunately, then STL extension proposal developers decided, okay, we are going to screw the core language designers and we are going to do something more. We are going to create a function that is able to call anything that is function-like, including the member variables and member function pointers and member variables. So if you're writing a generic code and you don't know exactly which type of function you got, it's better to use invoke instead of using just the m function open close. Okay? So yet again, if you're writing a generic function and you want to accept any callable, then you should probably use invoke instead of normal syntax for function invocation. Okay, so since before C++ 17, we didn't have automatic template deduction based on constructors and stuff like that. We usually had to write factory functions so that we can trigger the automatic template deduction, and then we don't need to specify make lazyval off and the exact type of the function that we received. Obviously, the make lazyval would not be needed in C++ 17 for this class, but since barely any compiler supports all of this stuff at the moment, barely any stable compiler, it's quite nice to write make functions until we get new compilers. So if we create a make function like this, we can use it auto answer equals make lazyval of some lambda or another function or anything else. But this is not quite the same as we started with. We wanted to have a keyword called lazy and just a block. So what should we do? Use a macro. How?
Open square brackets, close square brackets.
Not for this one. So the open, close, the diamond, the empty template stuff, that works in the STL for STL, less STL, all the operator wrappers, because they were designed for it to work. They have the deferred type deduction when the operator call is being invoked instead of on the class definition. Here we don't have the possibility to write just the empty. It doesn't work if you actually don't implement it specifically. And here we can't implement it simply because the constructor, hello? The constructor, this is fun. Let me try again. The type f needs to be known at construction time. For this thing, we can't defer the deduction to the call operator. Okay, yeah, sorry. Okay, but still we would have to have the close curlies, close normal, and semicolon. Because we can't, if we wanted to, for example, if we wrote just lazyval, we need to pass an argument to its constructor, right?
So may I say?
Yeah.
Maybe we need to overload the operator equals.
Okay.
And put it into a macro.
So something like that, yeah. Essentially, the only functions in C++ that you can call without open and close parentheses are the operators. So if you want to lose parentheses from something like this, you need to abuse the operators. So instead of the make lazyval function, you can create a structure that is called, as the STL usually does, make lazyval helper with an underscore in front, and you create a simple instance of it, which the user will never see. That make lazyval helper instance will have operator minus, which accepts a function. So it's just a dumb instance of a really dummy class that just defines the minus operator. And then you say define lazy, make lazy val helper minus head of a lambda, and that's it. And this is why I call it abuse. It looks really nice until you see what's behind it. And as far as the operator minus is concerned, you can put any operator that you want. I decided to go for the minus because Alexandrescu used minus at some point for his on-scope exit stuff, and so he had a reason, something related to operator precedence and similar stuff. So this was the first step, how to still not program functionally, but yet to have your code benefit from some kind of functional idioms. Now the next step is going to be how to properly use higher order functions. And before I go to that, the gift that I gave to one of the people who asked questions and forgot the other ones is a voucher for the book that I'm writing. It's currently in the early access program, and people from any gave me the CPP Russia discount code if you want to use it for any book in their store. But my book is much better than any of the others. Okay, and if you want to take a picture again, you have a barcode and everything else, so you get the link and blah blah. I'll show it again at the end of the presentation. So, just a second. Who was you and somebody else? Yeah. I'll leave two of them here and then continue. You can pick them up right now. Okay. So about usage. Now, one of the things that STL did quite nicely, we always had really powerful algorithms at our disposal. The problem is that the STL algorithms are not really that composable. They can be composed, but not in a sane way. And they tend to accept iterator pairs, and they then tend to return values through output iterator pairs that are arguments to an algorithm instead of a result. So some smart people decided to create ranges. And ranges existed in Boost and now Eric Niebler's ranges and everything else. Now, before we continue on a specific example, a long time ago, Donald Knuth was asked to implement a program for one of ACM's journals. And this is one of the most famous stories related to how Donald could fail. And so the idea was he had a text file, and he should write out the, for example, 10 most used words in the text. So he wrote a really detailed and awesome implementation in Pascal. And it was 10 pages long. It had a lot of documentation. Obviously, it had novel data structures and everything else. So it was exactly the solution that you would expect from Donald Knuth. It was beautiful and worked perfectly. And at some point, when he submitted it was a custom for that journal to ask another person to give a critique on the work. And obviously not a lot of people can give critique for Donald Knuth's work, but Doug McIlroy managed to send just a few lines of bash of Unix shell scripting that did exactly the same as the 10 pages long Pascal solution. So what's the point of this example at a C++ conference? Simply because this is a completely functional and beautiful solution. You have an input, you have one transformation, then you compose it to another transformation, compose. In the end, you got the result. You don't need to think about algorithms. You don't need to think about all the steps that you need, all the structures where you need to save your data. You just need, okay, I can split my program into let's clear the output, remove all the special characters, leave just the letters. Remove, I don't know, put everything lowercase, then sort them, group them, and everything else. And so it should, functional programming should usually look like this, like a conveyor belt. You have the input, then you have a couple of machines that transform your input until you get the finished product on the right. So let's see what would it look like in C++. So we start with a huge chunk of text. Then we want to remove all the special, all non-alphanumeric characters and replace them with \n, so that we just forget everything and all the words will be in separate lines. After that, we can say transform to lower. We all know what std transform does. This does essentially the same, but in a little bit different syntax. It gets the input from the left side of the bar and gives the output just like bash does. After this, we just need to split. We are going to get word by word, then sort and group by. When we sort them, we will have a lot of the same word repeated. When we say group by, we are going to get, let's say, a list of lists or a range of ranges, where first item in the range will be all the words called A. The second item, a range of A's. Third item, a range of S's, and so on and so on. So now we have all the words sorted and grouped, and we don't really need all the repetitions. We just need the count, and we need the word itself. So again, we just push it through a transform, convert each group to a pair of count and the word. Okay? Again, sort, and because sort uses ascending, we want it to be the other way around. We reverse it and then just take, for example, 2 or 10 words, depending on how many we wanted. So the whole program should be able to look something like this. Instead of 10 pages of Pascal, you have just a few transformations of the original data. And now you probably noticed the last line on the slide that says almost compilable due to range v3 design. People who were yesterday on the workshop know what this almost compilable means. If you try to compile this, you're going to get 1 kilometer of errors because of some strange design decisions, generally influenced by committee, not what Eric Nibbler wanted in the first place. This cannot be in one chunk of transformations. Every time that you call sort, you'll need some sortable collection in front, so you need to convert it to vector first and then sort. And then you'll need to define a completely separate variable to work on the previously created chunk. But that's not something that I want to talk further today, because people yesterday were really annoyed by all the compiler things that I have seen. So the first section was how to abuse functional programming. The second section is how to use it in your everyday work. And ranges are really powerful and really useful, because you know that STL algorithms are, and this is just a better version of STL.
Excuse me, I can't help. I can't help but notice that this is horribly inefficient. Second sort is not needed as a single pass walk until you get the first 10. First sort,
that is true.
Strings all over the place.
And I do agree. This is, I wouldn't say horribly, but really inefficient.
Actually, none of the sorts are needed at all. If you were to just collect them in a hash table, you'd have a program that's much faster. And similarly with
Of
top,
course.
and similarly with top n, you need quick select, not sort. And if you had like 1 terabyte of data, we would fail miserably. So
of course.
it kind of.
So the example, I do agree with both of you. You don't need to explain yourselves anymore. But, do you both deserve? Or yeah. So this version, obviously, yeah, it is horribly inefficient. The second sort doesn't need to sort the whole of the collection. It can be implemented as a lazy sort. And the cool thing about this solution is that you wouldn't have to change this code in order to make it efficient. You just need to say, okay, the second sort should be done lazily.
Well, it should be a single pass. A single pass collecting a statistic, right? Collecting a tail of n.
I'm sorry?
You know, like in Boost Accumulator, you can collect a tail of n top elements in one pass.
Yeah, so I'm not claiming that this is a perfect solution.
Right.
But one thing that I can say is that it is 3 times as fast as Haskell version. And Haskell is used at least in Britain, in banks and everything else. So even the bad implementation is still quite efficient. Obviously, you can either optimize it through hash maps or whatever, or you can optimize it through using the lazy sort. And the lazy sort algorithm is quite trivial to implement, even based on quicksort. And now the third part is, if you're really, really, really hugely in love with functional programming, then you should probably accept the idea that all functional programming needs to be pure, that you should never have any side effects or anything else. And in C++, it's not really all that easy, because C++ is not made to be a pure functional, not meant to be pure language. So, okay, do we all know what pure functions are? Okay, let's skip referential transparency then. So, what's the problem with mutable state? John Carmack, at some point, you should probably read his blog, Functional Programming in C++. He made a nice article. Mutable state is difficult to reason with even if you don't have threads. And when we are in a multi-threaded or concurrent environment, then it becomes much more difficult because we need to know what needs to be locked at any point in time. So instead, when we have, for example, a normal application, it has a user, it has the program state and the UI. Just a simple thing that is called onClicked can have this many connections. So the user clicks on something, so the function is called. Employees view visible true affects the UI at the same time. The UI affects the state because it needs to load the data, and so it can be really tangled. So your components are not that divisible from one another. It's not a good encapsulation for the software. If you have immutable state, you can't have these chains of influences because you cannot ever change any data. But then again, okay, let's skip a few of these. How can we program the world and not change it? And when you get the slides later, read all the quotes. They're really inspiring and really beautiful. Yeah.
I hate to say it, but you could use monads.
Yeah. My first talk at a C++ conference was about monads, and after that I decided to put off a bit because people didn't really like the idea that much. The effects that it has, yeah, but all the things in the background, not so much. So if we have the world and we are not allowed to change it, how can we?
we save state, copy to new one, and pass new to next function call.
Okay. So that's one of the things that has been covered since ancient Greek and in a lot of modern movies. Anytime you make a decision in real life, you're not actually changing this world, but creating a dozen of parallel worlds. In one, you made that choice. In another one, you made some other choice. So if we leverage that idea of multiple parallel worlds and that all the worlds are immutable, then we can do it in C++ as well. So instead of changing the world, we are creating a new one. Again, we can create a dozen of new ones, but we usually just need the one. And now the question is, yeah, but copying the whole world each time that we do something, it must be really, really slow. And C++ allows us two options how to solve this. One option is to provide the API that looks like it's creating the new world, but the API that cannot be ever called on a non-temporary object. So if you want to create a function for which is, okay, so we have a world, we want to change how many people exist in the world, we would have a function called widPopulation. And the function widPopulation should return a new world with that population. If we declared it as normal world something const, it would allow the user to duplicate the world as many times as he wants, right? But with it, if we leverage R-value references, then we can force and say, okay, widPopulation only exists if this is an R-value reference. All right? So in this case, nobody would ever be able to copy the object. The user will always need to destroy the old one while creating the new one. And still all the purity is preserved because no data is ever mutated. The new world is the new world, it's just that the previous one will never be used and is killed. So if we wanted to use something like this on something that's an L value, we would need explicitly to state move previous world dot widPopulation, which explicitly tells the compiler and all the other members of your project, okay, and after this line, the old world will never be used again. All right? So this is the way to force the compiler not to allow us to create copies. But then again, copies can sometimes be useful. Just imagine that instead of killing all the previous worlds, you still have all the 1,000 of them. And you find a bug in your program. You just need to check the previous world. You can go travel through time, just like a GDB reverse debugging would do. And at the same time, you can create multiple worlds where you made multiple choices, so you can test different stuff, different scenarios at the same time, or even somehow merge the results that you got from 1,000 parallel worlds into one. So sometimes creating copies is actually useful. But if you use the std vector, std string, and everything like that, it would be really, really inefficient. So for that, there are a lot of data structures that are designed to be efficient for copying and slight mutations. We are going to start with the simplest one, which obviously none of you will ever use. Okay, not ever. One guy yesterday mentioned that he actually had a benchmarked use case where the lists were faster than anything else, with custom allocators and everything else. So the point here is not that list is good, but to show the general principle of how most of the persistent of functional data structures work. So we all know what a linked list is. If we wanted to create a new list in C++ for a normal linked list that has one element prepended to it, we would copy the previous list and add an element in front. But if we say that all the lists that we have ever created are not mutable, then we don't need the copy. We can just create another list with a single element which points to the previous head. Now in our program we have two lists. One, the old one, the new one that has one element prepended. Because they're both immutable, it will never be possible for somebody to change the L1 and automatically change the L2. Okay? So because the data is constant, you can share it freely.
If you use a unique pointer here, then you can't have two pointers pointing to node A.
Yep, that's why it's in red.
Oh.
So to repeat, because the usual implementation of a single linked list is to use unique pointer. When we want to change it to this, the unique pointer becomes red. Because now A doesn't have a unique owner. It needs to be a shared pointer. But when you mentioned already that problem, what is the other problem of using unique pointers or shared pointers in the list implementation? Yeah? Essentially, if it's a really long list on destruction, you're just going to call the destructor, it will call the destructor, and you will offer your stack. So this will never be a proper implementation for a linked list. But we don't care because we don't want to use the linked list, just to explain the concepts of data sharing. So what happens if we want to, okay, again, prepending or getting the tail. What happens if we want to append? Can we do this? No, this would change all the lists that currently exist. So in the case when we want to prepend something to a list, it's efficient. If we want to append something to the list, we actually need to copy it, and then we can share its data with all the derivative lists of that one. If we want to insert, we will have to copy all the nodes before the inserting place, and we can share all the nodes that are after the inserting place. Okay? Any questions?
Then link structures.
Yeah. So this was a short answer, right? Essentially, the only place where you need any kind of synchronization here is the reference counting for the shared pointer. So I would use transactional, well, whatever. I do agree. So now memory handling. If these are shared pointers, if the head of one list is destroyed, it will take all the other nodes that doesn't have another parent automatically, unless it overflows the stack. But lists are not really efficient. So getting the head of a list, getting a tail of a list, prepending an element, these are all O of 1. But appending, concatenation, and most of the useful things are O of n. And not only that, lists are not cache friendly. So we should probably devise some special data structure that is able to leverage cache, that will have all the same efficiencies as std vector. Obviously a little bit slower, but for all the things that vector is O of 1, our structure should be again O of 1 and similar. And one of those the data structures that has emerged quite recently is called bitmapped vector tree. And this is not the only name it has. It has at least 5 different names, but which will make it a little bit harder for you to Google it. But if you write this, you should probably end up on the right page. So what's the idea? You define the size of a bucket to be, for example, some power of 2. Usually it's either 32 or 64, but for the sake of the slide, I just took that the limit is 4. So you use the STD vector that has the most, at most 4 elements, or STD array or whatever. When you want to put one item, you create the block of 4 elements and put one item into it. If you need 3 items, then you put 3 items. What happens when you overflow the bucket? You create a new one and continue packing the items inside it. Now, since we have 2 buckets, we need a way to keep the track of them. So we are going to have to create another bucket of the same size that now doesn't contain values, but just points to the buckets that actually do have the values. Okay? And again, when it overflows, you create another level, and you get a tree. Now, what's the special about this tree compared to all the trees that we've ever seen? Because lookup is really trivial. If you have an index 14, you want to get the 14th element, you just need to chop it into segments of bits. You use the first segment as the index in the top layer. You use the second segment as the index in the child, and the next index for that child. And this is why it's called bitmapped tree, because trees are usually really structures that tend to be efficient when you're searching for specific keys. And here, the index is the key. The bits in the index are used as chunked key. And the good thing about it is that if you use the 32 or 64 buckets, then you have no possibility to go over six or 7 layers. So you have an upper limit. If you take all the memory in your system, you have the upper limit of definitely less than 10 layers that you have. So the lookup can have at most 10 steps, which is O of 1. It is obviously slower than vector because it has to jump through hoops, but at least the copy is super efficient, and this is still O of 1. A little bit slower O of 1, but still O of 1. And if you wanted to create iterators on this thing, they could be much more efficient than each plus plus going through all the layers. You just point to an element in the leaf and move it until you reach the end, and then jump to the next one, jump to the next one. So iterating would be almost as fast as STD vector. And the good thing about this is that since these are the buckets, they're chunks in memory, and they're really, really cache friendly, unlike lists and like STD vector. So we already seen how, if we wanted to create this as a mutable data structure, how we would add items to it. So in this case, we have the starting one, we append P and append Q, and the data structure just grows. Now you have just to look at which parts changed between all of the 3 structures. You just need to do whatever diff does when you compare 2 versions of the code. The only thing that changes is the path from the root to the leaf where you want to put your item. Every other node in the structure is shared, is the same, it doesn't change. So if you wanted to create the immutable version of a BVT, it would look like this. So the V1 is what we already had. V2 just needs a new root and a new leaf. And the new root will point to all the elements from the previous data structure, from previous instance. And just the new things will be created. So again, this is appending, which is essentially O of 1, allocating at most 10 things on a path and nothing else. So as appending goes, it might even be more efficient than the worst case scenario for a vector, the case when it actually needs to copy all of its data. And again, if you fill all the leaf items, you need to create a new root. And again, the only new nodes that you have created, new root and the leaves, the nodes up to the leaf where you added your element. Everything else is shared. Okay? So now we have 3 completely different versions of V1, V2, and V3, 3 different worlds. And this is still quite efficient. Both memory efficient and algorithmic. So a few of the zoomed in examples. If we have room in the last leaf, because when appending we always add to the last leaf if it has room, we are going to duplicate the room and add the element. So just mem copy the bucket or construct copy the bucket. Then create all the parents and point them to the previous structure. If the buckets were full, what do you need to do? Create a new bucket. Put the element in there, create its parents, and point them to the previous ones. And the last case, if all the leaves have been filled and all the nodes have been filled, then you need to create a new root, because you don't have any more space to add new buckets in the previous data structure. So what do you create here? Again, the leaf that holds the data, its parents, and everything else that points to the previous structure. So the efficiency of this structure is really nice. You have direct access by index, almost direct, it's O of 1. Appending an element is O of 1, updating any of the values inside it is O of 1, even if it actually creates a copy of the data structure. And the only inefficient things are prepending, concatenation, and inserting in the middle. And they're O of n, just like with std vector. Okay? And the cool thing about this structure is that the same principle of having a tree and sharing all the nodes apart from one branch works on not only this structure. You can search, well, you can check out a book. It was first his PhD thesis and later he published a book. So Chris Okazaki, Purely Functional Data Structures. You have red-black trees that are immutable. You have everything with persistent or immutable versions. And that should be it for today. So questions? I don't have any more vouchers, so.
Thank you for your talk. It was very interesting. I wonder what is the most preferable way to handle errors in a functional way in C++?
To handle errors?
Yeah.
Monads. So
yeah, but when you use monadic error handling, you've got the other libraries which use exceptions or maybe error codes. So how do you integrate with them?
Very difficult. So if you're writing a library, then you can dictate whatever you want to use. If you're writing the client code and somebody is using exceptions, you can wrap them in. For example, you should watch Systematic Error Handling by Alexandrescu from 5 or more years ago.
Mm-hmm.
He was talking about std expected, which could contain either a value or an exception. And a lot of people evolved that concept into a little bit more sophisticated, and expected is essentially a monad.
Mm-hmm.
So instead of returning a value or an exception, if you actually want to force the user to check for the error, you just return expected of t.
Thank you.
At what scale do these kind of techniques work? I mean, does it work at can you make a really big system entirely in a functional way, doing it like this, or is it still like more piecemeal?
A lot of people have done it, even in Haskell, not in C++. So in a language that doesn't allow you to be dirty ever in your life. It needs a different mindset. So at the meeting C++, I was talking a little bit about designing reactive systems, and it's a little bit tooting on my own horn, but you can watch that talk. Essentially, you design your software systems to be like ranges, where each component is just asynchronous, and then again you have transformations of the asynchronous ranges. And a lot can be accomplished, which is really strange and really weird.
You kind of skipped over referential transparency. In C++, we can't really tell if a function is referentially transparent. And it is kind of important if you are doing a functional system with lazy evaluation, with any kind of memoization. Do you see it happening anytime in the future?
Unfortunately, I'm not that optimistic, because a lot of things that people proposed for standardization just went into vapor. And a lot of things just get lost. And a lot of things don't get lost, but don't get into C++ 17 even if you wanted them to be. So I don't expect that we are going to get, maybe we'll eventually get an attribute pure or whatever, but I wouldn't count on it.
Well, we can always take initiative, right?
Hmm?
You can always take initiative.
Yeah.
Make an implementation.